we have derived that probability that a randomly selected molecule has its velocity components, that is xyz component of velocity, lying in the range u and u plus du, v and v plus dv, and w plus dw respectively, and simultaneously is p, which is equal to fu, fv, fw, du, dv, dw. So the molecule will simultaneously will have velocity components lying in these ranges. Okay, and fu, fw are the distribution function at u, v, w respectively. Now we will find the value of this probability in a different way. Okay, so suppose out of n molecules there are dn molecules which have their velocity components lying in this said range. Okay, so out of n molecules there are dn molecules which have their velocity components lying in this said range simultaneously. For instance, so till now we have talked about only one molecule which is likely to have its velocity component lying in this range. Now there can be other molecules which are likely to have their velocity components lying in the same range. For instance, suppose in one class there are students, okay, and if you consider their distribution of marks, then it is likely enough that more than one student will have their marks in the, suppose, between 60 to 70. Suppose you can find one student who has got marks between 60 and 70. Okay, but it is likely enough that you will find other students, more than one student, who have got marks between 60 to 70. Okay, so similarly, in out of n molecules, it is likely that more than one molecules will have their velocity components like in this range. Okay, suppose number of such molecule is dn. Okay, so now what is the probability that you randomly pick one molecule out of this dn molecule? So there are n molecules and you pick one molecule which will be one of these dn molecules that it will have its velocity component lying in this range simultaneously. So it is similar to a problem that we have already discussed, that is this one. There are n gas molecules. Out of the n molecules, dn molecules have their velocities lying in the range c and c plus dc. And what is the probability that you pick one random gas molecule which has velocity lying in the range c plus dc? The only difference here that here the velocity in this problem, the velocity range is c and c plus dc, and here the velocity components are in the range u and u plus du, v and v plus dv, and w plus dw simultaneously. So in such case, the probability was dn by n. So dn is the number of way it can happen divided by total number of possible outcomes. N is the total number of molecules in the system, which is total number of possible outcomes, and dn is the number of way it can happen because there are dn number of molecules which have their velocity components lying in that in the said ranges. Okay, so similarly in here also the probability that you pick one molecule which has velocity components lying in the said range is dn by n. If there are n molecules and out of them dn molecules have their velocity lying in this range, then the probability that you pick one of the molecules of dn, you pick one of the dn molecules is dn by n. Okay, and we have already found that p is again equals to fu, fp, fw into du, dv, dw. So we can say that dn by n is equals to Fu, Fb, Fw, du, dv, dw. Okay, so hence the number of molecules simultaneously having velocity components lying between u and u plus du, v and v plus dv, and z and z plus dz is this one, dn by n into fu, fv, fw, du, dv, dw. So dn, so from this equation, in the next step we can write dn is n into fu, fv, fw, du, dv, dw. Okay. So now, how can we represent these molecules in the velocity diagram? Okay, so if you now we'll try to represent these dn molecules which have their velocity components lying in the said range, that is u and u plus du, v and v plus dv, w and w plus dw. We'll try to represent them in the velocity diagram. So you know, in the velocity diagram the molecules are depicted as velocity points. So the diagram that we have already drawn earlier, that is, we took this is the velocity point which represent a molecule having its velocity components u, v and w. So this is the molecule having velocity components u, v, w. But we want to depict the molecule, we want to represent the molecules which have their velocity components lying in the range, you know, u and u plus du and etc. etc. So the dn molecules have their x component of velocity not u but an lying in the range u and u plus du. So we need to go an extra du along x-axis because we need the range u and u plus du. So from u we go an extra du. Then for y component we need these molecules lying in the range v and v plus dv. So this is v, okay, and then we need to go an extra v along y-axis, extra dv along, suppose this is dv along y-axis. Then for the z component we need the molecules having the z component of velocity between w and w plus dw. We have this point w, z component is w, so we need to go an extra dw along z axis. Now what we'll do, so in 3D what will happen, that they will make one cuboid, and all these dn molecules will lie within this cuboid. Okay, so all the dn molecules in this velocity space will lie within these cuboids with sides du, dv and dw, which are parallel to ox, oy and oz axis respectively. So we can say that all these dn molecules which are represented as velocity points in this velocity diagram, how can we represent them? They will lie in the cuboid of sides du, dv, dw, which are along ox, oy, oz axis. Okay, so in generally in position space coordinate, each point will give its position. Okay, like xyz will give the coordinates, xyz will give its position, but in velocity diagram or velocity space, each point will give us this component velocity as a coordinate. So the coordinate of this point is uvw. Okay, coordinates of this point is uvw, and it will give us, it represent a molecule which has its component, velocity components u, v, w along x, y and z axis. Okay, so all the points within this cuboid will represent the molecules which have their x, y and z component of velocities within these ranges. Okay, so the cuboid has sides du, dv, dw. So volume of the cuboid is du, dv, dw. Okay, product of du, dv and dw. So within the volume du, the number of molecules is dn. Number of velocity point representation of the molecules is dn. So what is the number of molecules per unit volume? So we know that dn is equals to n FV/FW du dv dw. So if we do dn by du dv dw, which will be number of molecules per unit volume in the velocity space or the velocity volume element, it will be n FV/FW. So dn by du dv dw is n into FV/FW. So this is number of molecules in per unit volume, where the volume element is taken in a velocity space, which is so it is not an space volume, it will be a velocity volume. The sides does not represent a length or height, they represent the velocities, right? Du dv dw are velocities. So dn by du dv dw is a kind of a number density, which is now denoted as rho, which is equals to n FV/FW, which is called number density of molecules in velocity space.